Hi, welcome to the GATE lecture series on computer organization and architecture. The topic that we'll be discussing today is pipelining. Pipelining is the process of arrangement of hardware component of CPU such that the performance of the CPU is increased. So, as we all know, the CPU is completely a hardware component. So, each component has its own functionality. We are going to arrange the components of CPU in such a way that we utilize the CPU to the fullest, to its maximum efficiency. So how are we going to bring the maximum efficiency out of the CPU is what? Using this pipeline. And this, what we are going to do is, we are going to overlap the instruction execution. The instruction is brought into the CPU one by one. If it is executed one by one, it will be taking much time. So we are going to perform parallel execution. And how are we going to do that? How are we going to arrange the hardware such a way the parallel execution is possible? That will be seen. So this pipelining concept will be giving us an amazing speed up, amazing CPU performance. So we'll see in detail about what is pipelining. This is a classic example of pipelining. We'll take a real-time example and then we'll see the concept of pipelining first. This is a laundry example where 4 people have to wash their clothes and dry it up. There are 3 functional units available. One is for washing, other one is for drying, the third one is for folding. So, washer is going to take 30 minutes, dryer is taking 40 minutes and folder is taking 20 minutes each. Each of these are having different functionality and different times. So how these 4 people A, B and C, D are going to utilize this functionality with pipelining, without pipelining, we'll see the performance and we'll get to know what is the concept of pipelining. Okay, this is the execution without pipelining. So first A, the person A is going to wash the clothes, then dry, then fold. Okay, so the washing is taking 30 seconds, maybe in time unit, 30 seconds will give. So 30 seconds, 30 minutes, 40 minutes for drying and 20 minutes for folding. So to complete the work of A, we need 30 plus 40 plus 20, 70, 130. So 1.5 hours to complete washing by one person. Okay. Similarly, if we do it, so all 3 functional units are free now. We are bringing in the second person to do the same work. So again, the second person will take 1.5 hours to complete his work. Then the third person will come 1.5 hours and fourth person will come 1.5 hours. So if you see here, so the total time taken, if all these persons are doing the work one by one, the total time taken to complete the laundry is 6 hours, 1.5 into 4. So which means 6 hours for 4 loads is required. So this is without pipelining. So now let us utilize the functional units to the fullest using pipelining. So what is happening here is person A is taking 30 minutes to wash his clothes. Then he moves all the clothes to the drying unit. So at that time this washing unit is free, completely free. The hardware part here is completely free. So why to leave it idle? So this idle washing space can be utilized by B. So in the second time unit, if you see, B will be utilizing the washing unit and A will be utilizing the drying unit. And if you when the A's work is moving on to the folding unit, then both these hardwares are free. So C can be, and this work is also completed by the B. So C can bring in for washing, B can bring in for drying, while A is doing the folding work. So simultaneously we are utilizing the functional units that are available in parallel. So what is the total time taken here is 3.5 hours for 4 loads. So 3.5 hours, this is the maximum time taken that we are taking for calculation. So So the first is 30, the remaining we are calculating using the maximum time taken. The last is 20 units for time. So totally the time taken for completing the laundry process by 4 loads is 3.5 hours in case we use pipelining concept. So this is the classic example which clearly explains how do we utilize the hardware to the fullest. So this concept we will be utilizing in our CPU hardware components. Let us see how the hardware components are utilized. So what is the lesson that we learned here is, it is not that single task efficiency is increased. Single task function will have its own timing, but how pipelining helps in gaining the complete throughput is important. So pipelining does not help the latency of single task. It is not improving the time for a single task, but it is helpful in increasing the throughput of the entire workload. So without pipelining, in the laundry example we have seen, it takes 6 hours to complete, but with pipelining we have seen it is taking 3.5 hours. So the complete throughput is increased, and the multiple tasks are operating simultaneously. So simultaneous utilization of function unit is possible in case of pipelining. So this is the lessons learned. Now let us see how the hardware pipeline, how the instruction pipelining is being done in the CPU. Okay, so MIPS instruction. MIPS is an example for architecture, instruction set architecture. So MIPS instruction execution can be divided into these many phases. We have seen this in the lecture 1 itself, how components of CPU is executing an instruction. First, the instruction will be fetched from the memory, and the instruction will be decoded. The decoder instruction will then be executed in the arithmetic and logic unit. Then the memory access, if it is required by the instruction, is done. And finally, after execution, the registers are updated with the newly computed value, which is being stored with the newly computed value. So these are the 5 steps that are generally existing in case of MIPS instruction. Let us see the hardware part here. So this is the hardware part. Instruction fetch. If you see these we have seen in detail about all these components. PC is nothing but the program counter. Program counter is a special purpose register which will hold the address of the current executing instruction. Instruction memory. Here the memory is divided into, here we have seen that in the von Neumann architecture, the memory will have the instruction as well as the data. So this is the instruction memory, and this is the data memory that is available. So this is also a component, we have seen it already. And registers, these are small memory units that are present inside the processor. And whatever arithmetic and logic unit, these are adders, shift registers, and so on, all these. So let us see what is happening in the instruction. Let us see what is happening in each and every stage one by one. So first, what will happen in the instruction fetch stage? Let us see. So what is happening in this instruction fetch stage is, program counter will have the address of the current executing instruction. So we go take the address of the instruction that is to be executed. We go to the instruction memory, we pick the instruction, and we store it in the instruction register which is there inside the processor. So what is happening? We go to the program counter, we take the address, and we go to the instruction memory and pick the instruction, we put it inside the instruction register. So at the end of instruction fetch, what is the output we have? We have the instruction loaded inside the instruction register. So what is happening here? We go to the memory location of the address pointed by the program counter, and then we bring the instruction from that memory location, load it into the instruction register. And apart from that, the program counter will automatically increment to point to the next instruction. Okay, next instruction for the execution of the next instruction. So this is what is happening in the first stage. First stage, we bring the instruction that is to be executed to the instruction register, and then we increment the program counter to point to the next instruction that is to be executed. So the first step is done, instruction fetch. The second step is instruction decode. Instruction decode step, what do we do is, we decode the instruction that is present inside the instruction register, and we we load the registers with that values. For example, if a register is having, if it is an add instruction, it is the control signals for add instruction is generated and it is passed. And what are all the operands that if it is to be written inside the register or if it is to be brought in from the memory, everything is being done. So all the registers are updated with the values that are brought in from the instructions. Okay, so now the registers are being updated. Now, in the decode part, what is happening? The decode of instruction and access of the register file is done. Okay, now the third step, execution step. The values, the data from the registers are brought in. If it is an arithmetic and logic calculation such as add, subtract, multiply and everything, the data from the registers are brought in to the arithmetic and logic unit and the execution of that operation is done. If it is not an ALU operation, if it is a load or store operation or a branch operation, what will be done? If it is a load or store operation, we need to have memory access. So this is the data memory. We have to bring in the data from the data memory. So the calculation for finding the address from where the data has to be brought in is done, and we have to go to the data memory to bring in the data for execution. Okay. The next step is memory access, where load and ALU has nothing to do with this memory access. Like add, subtract and something. If we want to load and store some values into the memory, then we need this step. So we go to the data memory. In case we want to load the data from the memory, we bring in the data. In case we want to store the data, we do it here. Okay, so load and store operation, we need to access the memory, and that is taking place here in this step. Finally, write back. After completing the execution, the store operation has to be done. So the registers has to be updated with the final value. So write back of the registers has to be done. Okay, so that is what is happening. Update of registers from either ALU or from the data loaded. We have to update the registers back here. So these are the 5 major operations that are present in the that is the data part that we have seen. MIPS instruction execution. Okay. So now, how the hardware is altered for making a pipelined data path. Okay. So all these instruction fetch, instruction decode, execution, memory access, and write back operations, everything is same. Only thing is there are latches inserted in between each and every stage of the execution. Okay. So why do we need these latches? Is to store the intermediate results of these two from the previous phase. We need this buffer. Okay, we need this latches. Latches is a register or it's a flip-flop. It is a small memory unit which is used to store the intermediate result of the previous stage. Okay, so there is a latch between the instruction fetch stage and the instruction decode stage. This is called IF/ID. Similarly, instruction decode stage and the execution stage, this is named as instruction decode/execution. So latches are placed in between every stage. That is the only difference between a single cycle data path and a pipelined data path. Pipelined data path, what do we need is a latch in between, that is a buffer in between every stage, so that the intermediate result from the previous stage can be stored and it can be utilized. We'll see why this buffer is needed. We'll see in the examples later. Okay, so now this is the basic pipeline for MIPS. This is the instruction fetch, instruction decode part. This is the execution part. This is memory, and this is write back part. Okay, what will happen in the pipelining is this. Okay, now in the first cycle, your first instruction fetch will happen. Okay, so the fetch will happen and the fetch will be completed. That is, your instruction will be loaded into the instruction register. Second is that in the second cycle, the instruction fetched instruction is decoded in the cycle 2. So at this time, what is happening is the hardware of this fetch part, the functional unit of this fetch part is idle. So we need not leave this idle. We can utilize this for fetching the next instruction. So the next instruction fetch is parallelly happening while the first instruction is getting decoded. So this is how it goes on. We'll see in detail what is happening. So in the cycle number 3, if you see, the first instruction would have come to the execution stage, and the second instruction which we brought in the cycle number 2 would have come to the decode stage. Okay, now again the first stage is left idle. So what we do is we bring in the third instruction for execution. So this is how we does not leave any of the hardware component to be idle, so that the parallelism is done and the CPU is utilized to the fullest. Okay, let us see in a detailed data path diagram how this is done. Okay, now in the first cycle, the first instruction will be brought into the fetch instruction fetch functional unit, and the instruction fetch is done. And in the cycle number 2, what is happening? The first instruction would have gone to the decode stage, and this part is left idle. So in the pipelining architecture, what is happening is the instruction number 2 is fetched here from the instruction memory. So instruction fetch of the second instruction will happen in the clock cycle 2. Okay. Now in the third clock cycle, what will happen? The first instruction would have gone to the execution phase, leaving these two idle. So the instruction which we brought, the second instruction which is brought into the fetch in the fetch cycle, in the cycle number 2, is gone to the decode stage now. Again, this will be idle. What will happen now? The third instruction will be fetched and will be executed. So this is how it is done. We are not going to leave any of the hardware idle for any time, and we are going to utilize the CPU to the fullest by parallelly executing every instruction that are available. Okay, so this is what is happening in the pipelining execution of certain instruction. Now let us move on to the calculation of execution time in pipeline and non-pipeline architecture, and we are going to calculate the speed up. So what is the performance improvement we are getting in case of pipeline and non-pipeline architecture? So now let us see in first what is the time taken for this program to complete using in a non-pipeline architecture. Okay, so the formula for computing the execution time is very simple. That is total number of instructions into time taken to complete each instruction. So time taken to complete each instruction is calculated using the number of stages. So number of stages in case of MIPS instruction set architecture is 5. So let us assume that each stage is taking 1 clock cycle. So total time to execute one instruction is 5 clock cycles. So now total number of instructions here is 1, 2, 3, 4 and 5. So 5 instructions. Each instruction is taking 5 clock cycles per instruction. So total time taken is 25 clock cycles. So now if you see here, this is a diagrammatic representation. Instruction 1 is executed. So at the first clock cycle, the instruction fetch will happen for the instruction 1, and instruction stages is done one by one, and the complete instruction 1 will be done at clock cycle 5. Once this execution of instruction 1 is done, the instruction 2 will be brought in the clock cycle 6, and it will go till 10, and the complete instruction 2 will be executed, and that is how the instruction 3, 4 and 5 are brought in one by one. And the complete time taken for executing all 5 instructions is 25 clock cycles. So in a non-pipeline architecture, the execution time can be calculated using the formula total number of instructions into time taken to execute each instruction. So it is 25 clock cycle in our example. Okay, in a pipelined architecture, what is the execution time calculated? So for calculating the cycle time, each cycle time, we need to consider there are two cases available. Okay, so in the non-pipeline architecture, we don't have any latches in between the data path, in between the stages of the data path. Okay, but here in the pipeline architecture, we have the new hardware component that is inserted in between every functional units of data path. That is, the latches are there in between the each and every stage of the data path. So the cycle time, so case 1, if you see, all stages offer same delay. Suppose if say instruction fetch is taking 1 clock cycle, instruction is decode is also taking 1 clock cycle, instruction execution is also taking 1 clock cycle. So if all the stages are taking same delay, which means same time. Okay, So the total cycle time will be delay offered by one stage, any stage, because every stage is offering the same delay, which is including the delay due to the registers. That is, this register means the delay due to the buffer which we have inserted in between. So cycle time, in case all the stages are having same time lapse, is one stage plus the delay offered by the latches which we have inserted, the buffer that we have inserted. So that is the calculating, that is the formula for calculating the cycle time. Suppose if all stages do not offer same delay, in this case, how do we calculate cycle time? Is for example, for this is instruction. For example, say instruction fetch is taking 1 nanosecond. Instruction decode is taking 2 nanoseconds. Instruction execution is taking 3 nanoseconds. So every stage is taking different clock cycles. So how do we calculate the cycle time in this case? Is we take the maximum delay offered at any stage. Suppose say execution is the maximum delay that is being taken, say 3 nanoseconds. So we take the 3 nanosecond as the common common delay time along with the buffer delay, that is the newly inserted latches delay. So that is how we calculate the cycle time in case of different delays for each stages. Okay, so there are two cases. One, as we have seen, that the delay in each stage is same. Okay, the second case is the delay in each stage is different. So in that case, maximum delay will be considered along with the delay in the buffers. Okay, so this is how we calculate the cycle time. In case of pipelined architecture, the formula for calculating the execution time is number of stages plus total number of instruction minus 1 into clock cycle time. Okay, so that is substitute the value. Total number of stages in the MIPS instruction set architecture that we have seen is 5 stages. So the number of stages here is 5. Number of instructions in our example is 5. So n minus 1 instruction is considered. So 5 plus 4 into clock cycle time. Let us assume that this delay is common for every stage and it is 1. We'll assume it to be 1. So clock cycle time is 1. Suppose if the delay is varying, we have to pick the maximum delay and we have to substitute in this place. Okay, so we'll substitute and find the answer. So total number of stages is 5 plus total number of instructions is 5 minus 1. So n minus 1 is 5 minus 1, 4 into clock cycle time. We assume that in this example, we'll be taking 1 clock cycle for every phase, every functional unit. So into 1. So total number of cycle that is required, that is execution time is 5 plus 4, which is equal to 9 clock cycles. If you see this, this is the diagrammatic representation. So first instruction takes 1 to 5, second instruction 2 to 6, and go on. So completion of all 5 instructions will happen at the clock cycle number 9. So this is what is happening. Okay. So now, how do you calculate the speed up? We have seen this for the same example. We have seen in a non-pipelined architecture the number of clock cycles required, and the pipelined architecture what is the execution time we have seen. Let us compute the speed up now. Okay, speed up formula for speed up is time taken to execute in a non-pipelined architecture divided by pipelined execution time. Okay. So in our example, in this example, we have seen that for an instruction to execute in a non-pipelined architecture, it took 25 clock cycles. Now in a pipelined architecture, it is 9. So 25 divided by 9 is 2.7. And the important thing to be noted is the maximum speed up that is possible, that can be achieved, is equal to number of stages. So total number of stages in the MIPS instruction set architecture is 5. So in this example, the maximum speed up that can be achieved is 5. That is the concept. Okay. So that's all about pipeline speed up ratio that we have calculated. In the next lecture, we'll be seeing about the drawbacks, the hazards that are available in the pipeline, and what are all the ways to rectify the hazards. Thank you for watching this video.